Okay, cool. So this is a pretty short talk. This is about half an hour. We've done one of these before. It's about an hour's worth of content, so I'll try to go quickly and move through it. But our slides provide more details, so you can always go back into those, and you can find those in a lot of different places. So top 10 data science practitioner pitfalls. I'll go ahead and get started. The first three are actually going to have a similar theme. So we'll start with train versus test. And this is analogous to overfitting is going to be this theme of the first three. And so that's making sure that our models are doing the right, that they generalize. So train versus test is a way of splitting your data. So in machine learning, this is the most common way of protecting to make sure that your algorithms that you fit on the data will generalize to data that they have not seen. And so what we're going to do is we're going to split our data when we get it in some chunk. There isn't really a standard. I often use 90-10 or 80-20, 70-30 is fine. But what we're going to do is keep that, let's say 70-30, we're going to keep that 30% partition away from the algorithm until we're done building it. And then we're going to test how well the algorithm that learned based on 70% of the data translates to the 30% of the data. It's a very common technique, very easy to use, but it's very common not to use it. And so you'll see most of the good algorithms will tend to overfit their data once they've and you want to make sure that they're not doing that, and this is how you keep that in check. And I'll actually show you a plot here of what overfitting means. That's really the theme of these first three. So we have a chart over here. The blue line is going to be representative of that 70%. This is what the model is seeing. So the blue line continues to go down as far as error. So low error is good. So it's continuing to get better. But when we withhold a part of the data, we see that at some point it looks like about 20 in this generic model complexity. This would be trees in some of your tree algorithms, epochs, and maybe your deep learning. It's going to start getting worse on the data it hasn't seen. So it's actually going to start, I think of this as memorizing the data. That's what a lot of our algorithms will start to do. And you don't want them to do that because memorizing the data doesn't translate to new data. So you want to find the patterns as broadly as it can such that it generalizes to data it hasn't seen. So train versus test is going to help you make sure that you're testing on data it hasn't seen. A validation set is one step further. So now we're going to talk train, test, and valid. I would say it's very common to use just the train test split. So what is the valid about? It's about holding a third set, because in machine learning, a lot of what you're going to do is follow this iterative process of building a model. So you're going to use your normal train test. So you're going to train a model and test that it's doing well, but you're often going to do this many, many times. You're going to try and set parameters in there. I use trees a lot, or GBM specifically has several hyperparameters to tune. So you're going to go find your way through that hyperparameter space, always doing this train test. So you're going to look at the test. After a while, if you're using this to guide what your best algorithm is, you may have overfit the actual validation set itself. And so there's a couple different ways we go about that. That's the next slide. But setting aside one almost under lock and key validation set, that when you're all done and you think you have your model that fits this data correctly, this could be over a day, it could be over weeks and months, then you check your validation set. So you're very sparingly checking that. And you just want to make sure that what you think, based on commonly using this internal validation, still works on data you really haven't seen and you haven't used yourself. So model performance, again, is how you're checking what it's doing. So you had that chart that was looking at generic error, but you want to think about what error works for your problem. And one common method of going and doing the train and test automatically to make sure that you have a more representative sample is going to be this k-fold cross-validation. That would pretty much be the standard of how you protect against overfitting. 10-fold cross-validation is very common. And so what it means is you're going to break your data set up into even chunks, and then you're actually going to run a model architecture, which is a set of parameters against each one of those. So you're actually going to build, if it was 10-fold cross-validation, you're going to build 10 different models, each time withholding 10%. And you're going to see how well your error generalizes across all of those 10 folds. So all of those 10 models predicting against a 10% that these models haven't seen before. That's k-fold cross-validation, and that would certainly be, and we enable that automatically in H2O. You can just drop a number in there, 3, 4, 5, 10 if you want 10, and it will automatically do that. And what it'll actually do, to get into what H2O does just a tiny bit, it's going to build that same architecture that you said that you want to apply to the full data after it's done. So it's actually going to run k plus 1. So if we specified 10, it'll build 10 different models, and you can see how the error is consistent across those or not consistent. If it's not consistent, that's where you have to get involved and understand what's going on. But if it is consistent, then it's going to fit one model to all of your data in case that's what you really want, so that you can use all of the data in one single model, but you have an estimate of what that final model should perform against new data that you may have not seen either. Down here we have some performance metrics, and you kind of have two classes here. So if we're doing regression, which is numerical prediction on a continuous variable, common metrics there, R-squared, mean squared error, mean squared error, although kind of in the same ballpark. I would also add to that mean absolute error as a common one. Classification, there's a lot more metrics, and the interesting part is these are it's more specific to what problem you're defining, I would say. That's arguable, but so we have accuracy, that's common, like how well did it do? If it guessed true, is true the correct answer? But we can get a lot more specific about that. So F1, H measure, log loss, those are different measures of your probability. So commonly people will fit a model, pick 50, think that everything above 0.5 means true, everything below it means false. But you can tune that yourself, and that is going to be really important to some of you that may have really unbalanced problems. So you want to fit the problem that you have and pick the right metric that matches. So now moving on, class imbalance is another one that can be tricky. We get a lot of questions about this, a lot of people trying to think what the right thing is to do here. So class imbalance is if we have where one of the classes is not represented as the same as the other. So if in a simple true-false, if true was occurring only 1% of the time and false was 99% of the time, we could call that imbalance. There isn't really a hard and fast rule for what imbalanced is, and I tend to not be concerned until it gets pretty low. In the ad tech industry, you're going to see far less than 1%, to several orders of magnitude. So what do you do about that? People typically, we have some simple remedies over here, which would be people try to rebalance the data set. And some algorithms won't even find, they'll be based on SVM, you see this sometimes, where if it's a 199, they will never guess the 1. They'll simply say, hey, okay, I can guess false all the time and be very accurate. And so people will tend to oversample the minority class, so maybe they'll take the 1%, copy it several times and bring that up so that it's closer to the 99. Or you can do the opposite, which would be to downsample your majority class. So you can take that 99 and bring it down closer to 1, or you can do both. We have a button in H2O that will allow you to do that. So a balance classes button. And so it actually will rebalance for you. It gives you some settings on how you want to balance of oversampling, undersampling. But one of the pitfalls in here is doing that, you've translated your actual problem. So if we go back to the train, test, valid, you want to be very careful not only to do that on the training data, because the point is it needs to work on new data that you've seen. And so you want to make sure and do that correctly. And again, the H2O balance classes does that. It will change the model in training, and the validation set will leave alone untouched. And when it does its predictions, it will show you how the error is. So we actually have to do some things with probabilities to downgrade those to try to make them more on what your actual regular probability space is. Categorical data is next. So categorical is just something other than continuous variables. Trues and falses would be one, state codes, something like that. And why this is a pitfall is that very commonly you see that you have a lot of them. And so different algorithms handle these in different ways. The most common way of handling these is simply to create numerical columns for each one. One-hot encoding, binarization, there's a few terms for this. But if you had state codes in the US, that would leave you with 50 different columns, which are just a 0 if the observation had that state, and 0 if it didn't, and a 1 if it did. So you'll have 50 columns, and only one of them will have a 1 in it. And a lot of your data sets have far more than 50. But this is what a lot of our algorithms do. We'll do that under automatically baked into our GLM and deep learning is that's going on. In some of the languages and some of the R, you may have to do that yourself. But the too many categories itself becomes a problem because you've created this sparse problem, and just different algorithms perform differently in that space. So I would say, as practicing data scientist, if you can, you want to try to reduce that dimensionality if you can. So we have a couple things here listed that if you know your data and you know there's this hierarchy there, try to understand how your model performs throughout that hierarchy. And you may want to see it, try to have it lean on some higher level hierarchies. If you can put that into your data, that may be a good thing to try. But there's a lot of techniques for doing this as well, specific dimensionality reduction techniques. So we offer PCA as one of those. GLRM is one. There's a talk about that. It's a really neat algorithm that's coming out that helps you with categoricals and numerics, so it actually works in both spaces. So things to do so that your categorical data doesn't kind of destroy your model. This curse of dimensionality can be difficult for models to fit. So understanding your data, understanding the levels in your categories can be important, and you'll probably tend to focus on what happens there. So missing data, let me check time. So missing data is a really common thing. We see a lot of people having problems with this, a lot of what to do with missing data. So if your observations in your data set is missing, there's a couple of reasons why it may be missing as well. Sometimes it's that it wasn't collected, and sometimes it's not applicable to the actual reading. And so I think understanding your data and knowing what you should do in these cases is probably right. You could actually think of partitioning your data set, if that makes more sense, so that you have things that don't belong all grouped together. You probably need a high enough population of that for it to make sense, but that actually can be a good idea for something like a GLM, which is otherwise going to impute. So the common way what actually people do with missing data is impute it. And there's a couple different imputation strategies for that. Some people will go to the point of using a random forest. GLRM actually is a good imputation method. The most common way of imputing is just to pick the average. So to pick the mean if that fits your problem, the median if that fits your problem, or the mode even with categoricals. But it's kind of a simple way of imputing something so that these algorithms can work on it, because GLM simply won't work with missing data, the standard GLM, unless you're in a sparse implementation. So I would say what to do. It kind of depends. Try to work through your data if you can, if you have a few of them. But it's common to see data sets where you're missing a value in some column for every single record. So you can't throw them out. I kind of skipped over that. So a lot of the algorithms sometimes will just reject those. It's most common in R to just omit the NAs. But if you have an NA somewhere on every record, then you have no model left. And it might not be the right thing to do, even if 10% only had missing. So these are some strategies for dealing with that. But understanding how your algorithm works, too, tree-based models is one of their biggest strengths. Tree-based models don't really care. You still may want to impute, but most of the time you can just keep going, and tree models understand that they handle that very gracefully. And our model specifically will check, and they will always resort to false, which means they go somewhere. The model is effectively fitting that. And it can't even fit NA as in a category all by itself, which sometimes is exactly what you want. You want to actually group those that didn't have a value together. So outliers and put in extreme values. This is another one that causes a lot of people a lot of data prep headache. What to do with these. And so an outlier, there's again no hard and fast definition for what an outlier or an extreme value is. And it can exist either in what you're trying to predict or even the things you're trying to use to predict it. It's most dangerous when you're trying to predict it. But there's valid outliers and invalid ones. And you want to kind of know which of your problems you have. So if you have a sensor that you expect the readings between 0 and 100, and then you get 10,000, that's likely the invalid outlier. And so what you do with that, perhaps you want to throw that record away. Maybe the entire record is something you want to get rid of. Or maybe you just want to correct that one value. Maybe you want to pick the max value or delete it if you can handle that, put an NA or something. But you probably want to do something to that value. Now, if it's something that is valid, like house prices are a good example for that. So a lot of us know that the median house price is the biggest index, and the reason why is that housing prices almost have no end on the high side. And so what you'll have is a $20 million house almost corrupting what people think of as the average value. So we use median to do that usually there. Here, what you want to do is understand how your algorithms are performing against that. That's a valid outlier. The price isn't wrong. It is correct. But you want to take that into account and know if in solving your problem, if you want to optimize to try to make sure that you're most correct on that value, then maybe you actually stay with a traditional algorithm which will solve in squared error terms. If you don't, you may want to do something different, like use a more robust measure. And that median would be a good example. And where we bring that in machine learning is using absolute error is the way to try and handle that sort of thing. Or you can just cap some of the values to try and protect against that. But understanding how your algorithms are working and what your cost measure is as you're doing this is probably just what you want to be cognizant of when you're going through these models, of how that's having an effect on your problem. And so what I'd really advise is just trying different strategies out. So taking these strategies and see what works best for you on that very same upfront train, test, valid type framework. Apply a technique, see if that gets you a better prediction at the end of the day. Data leakage is kind of a tough one. data leakage is really something that happens within the train test valid. The easiest way is, so leak is to effectively give your model something that it won't, train your model on something it won't have when you go to actually make predictions in a real production setting, which can, depends on what your setting is, but if you're going to train a model for weeks or months and then deploy it in a real-time scenario, you want to make sure that all the predictors you fed to your model are going to be available at that time. So it's common to accidentally leak future results into your model. It can go in sneaky ways, it can be in obvious ways. I think the sneaky ones are the ones worth more attention, and so we see things like data warehouses that'll put timestamps and will later get a record and show you the record as if it exists all along. And then you deploy in production, and this feature is blank or missing, and you weren't ready for that. This is an interesting scenario. So while you're at least fitting your model, you want to really, I think, look at the predictors if you can and really understand, am I going to have these available? Work with your production setting. Make sure that your API is going to have these things coming in. But also just sensibly look at the data and understand, is it reasonable that I would have this value at the time that I'm predicting? And simple leakage, you'll see this in like an airlines demo. If you're trying to contort a problem to solve one thing, but you have other variables that hint at what that was. So looking at a delayed time. If you know that the flight was canceled, then you probably also know it was delayed, if that's the way it's captured. So you need to remove that from, it's not reasonable to have known that the flight was canceled by the time you're trying to predict a delay. So there's this thing I think is very pervasive and very difficult to understand until you put something in production. And I see this in the competition world all the time, but it's a very real world problem. Useless models, this is one of my favorites. So if we look at data science as almost the art of data science and the entire continuum of it, I think setting up your problem is one of the most important things, and yet there aren't a lot of good lessons on how you do that. So what I really mean here is solving the wrong problem. So someone told you that they wanted to solve for the best prediction of the housing value, but when you really get to work with your customers, you really want to they want to understand something that was more of, well, only in this state or something like that. And you created a model that feasts off of some other things. And so you want to sit with them and really understand what the actual model is you're solving for. And you may be aiming at the wrong target. You may need to aim at a transform target, something like that. So maybe they tell you, I just want to know good from bad. And when you really discuss this with somebody, well, they want to know the different gradients, and maybe there's a different way that you can actually represent the data. And if you aim at that at the way that doesn't fit their problem, you can spend weeks or months trying to solve something that when you deploy it, it isn't very reasonable. It doesn't actually do what somebody wanted to do. So this is similar to software engineering, is to doing what the specification said, but also making sure that the specification does what the customer wants. The last one is no free lunch. So pervasive in machine learning. No free lunch in our context really means there isn't one single algorithm that is the best. I like to use GBM as a sledgehammer, but it isn't the best for every problem. And so it's nice to try. So we offer several different algorithms in H2O. Some people have constraints that will require you to use a GLM for transparency reasons. But even if just accuracy, if you're doing image recognition, like neural networks are really where you need to be. It's not a good idea probably to try a GBM random forest, a tree-based model. There's a lot of different problem sets, and we do have algorithms tailored to those problem sets. Unfortunately, that means that you kind of have to experiment with your models. So we have many different models to try them out, and some of those can have different settings, but you're not going to see the textbook for how to do this particular thing. In some niches, I think you can. I mean, there are some that are just, right now, you can try a convolutional neural network on image recognition. It's a good idea. But also, deeper than that, I think you see that the general heuristics even that you can learn. So even if you learn a good way around a few big models, or maybe you've researched your problem space and there's a specific algorithm fit to this, I've just found time and again that even these things we learn about the algorithms aren't quite always true, and you almost have to recheck whether it fits your data. I think at the end of the day, machine learning is very specific to each data set. We have a lot of good general purpose tools to help you around that, but tweaking knobs and levers is usually a good idea, especially if you care about accuracy to a few decimal points. So an example, we have a couple of them here. So tree models, we're told that they work equivalently with any order-preserving transformation. So why would you take the log of a predictor, because it really doesn't matter, it moves left to right. But in the implementations, it actually does matter sometimes, because they're not doing exhaustive searches around the whole thing. So we're always fitting a distributions. So generally, you can not worry about your distributions with tree models, and we'll certainly talk about that when the GBM talk comes up, and random forest. But after a while, if you were really living with your data set for a really long time, I find that testing some of these things, tweaking some of these things, you may actually find that you will get better performance by going against some of the conventions a little bit. What to do about these? Yeah, understand how the underlying algorithms operate. GLM is going to operate very, very differently than a random forest. And so you'll get an intuition of how they do, although we're trying to make it easy for you to deploy, to try many of these. That's definitely one of the focuses we have, is to allow you to experiment really quickly with the algorithms in H2O. But that's the case in any language, any implementation. You want to be trying different things until you can slowly build up that intuition of what works where. But I find even when you do that, you get challenged. So feature engineering and feature selection, I don't think, deep learning, the promise of deep learning is that we won't have to do this. I think truthfully, you always do. If you're pulling data out of a database, you may exist at a higher hierarchy than where your data does. So you want to predict something at a person level, but you have all of their itemized receipts for an entire year. But your prediction is something on the person level. So deep learning can't solve that. You have to help it out and roll up those, all of that granular detail into a person level, because that's where the target exists. So your machine learning model, to frame it correctly, is going to be where your targets are. And very often, your actual data doesn't exist at the same level of granularity as where that targets are. So I think feature engineering, feature selection become very important, even with the algorithms we have. A lot of these models are getting good. Like a regularized GLM will help you with, you can throw a lot more things in there, and if you put a heavy L1 penalty on there, it will reduce the features that it uses. So it will help you through that feature selection process by doing it for you. But just the same, you can usually help these algorithms out if you put some common sense into it, if you understand your data as well. Interpret and react to the model feedback, and that would be almost the main theme here of what to do to avoid a lot of these pitfalls, is to develop that nice train test validation loop and understand the consequences of all these actions you're doing. And so I would almost advise running with a very simple baseline. Jam the data in, see what happens, and then start to make some of these statistically sound transformations to your data, doing log transforms, or you're trying a few different ways of using different scoring functions to see how that affects your end-of-the-day model. And that would be across all of these. All of these techniques, if you can get a good experimentation loop going, then you can apply some really simple code to try to attack what you think is a problem. And oftentimes, the machine learning models are very good. They don't need that thing that you thought they did. Sometimes they can be worse for it. So understanding how everything moves on time, I think, is very useful. So I guess maybe I went too fast. So we still have some content. But that gets us our top 10. We have some slides. I took down some of the content here. We have a bigger version of this as well that is a little more prescriptive about some of the techniques. But I think a lot of these are covered in elements of statistical learning. And we've tried to make sure that in H2O, you're actually handling these as well as you can. Where we do have something that looks close to a prescribed method, like balanced classes, train test validation, we make all these very easy for you to do in H2O. So when you load a data set, you can split it right off the top, and you can pick any of the distributions, so you can split it 75-25. So it helps you kind of do the right thing, and validation is automatically done while you're model fitting if you want to deploy it. So you don't even have to worry about scoring the models, fitting a model and then predicting after the while just to see how well it did. It's going to be baked into the product that if you provide a validation set, it will automatically show you how that error moves. And that's really powerful on a tree-based algorithm or something that's iterative, because you can see the asymptote of your performance, or if we go way up on the slides, where we started to overfit that data, we're actually going to show that to you. And you heard Arno talk in the morning about something I'm really excited about, which is the early stopping criteria. I think that's going to be huge. It will help you, so you can set it to protect against overfitting automatically yourself. But you can watch your algorithms work and do this train test validation to make sure that your algorithm isn't starting to go too deep on your data and fit that specific data set too well. I guess with the remaining minutes, if we want to do question and answer, if anybody has any questions. Yeah, that's tough. So yeah, if you look at your train test validation, if that, so I think the best one would be first to take a third cut if you can. Now you may be talking about even if you've taken the third cut, what do you do if this internal validation of your specific model doesn't generalize to the other one? Then it is kind of back to the drawing board, and it is difficult in that sense. So I don't have a great prescribed method for what to do there. I think you almost have to look at the validation set to a certain extent. And maybe what you might want to do without looking too heavily at it would be test distributions. Because we'll use a random distribution most of the time to run our train test validation, but we give you some options to do that. And every problem is a little different. So sometimes if you have a temporal divide, if there's a time going on, you can try as hard as you can. Maybe next month's data just looks different for some reason. Hopefully, if that's gone on, you can collect more data and use another month or something, but that's not always realistic. So I would say the first place to check would be distributions. First of your target, that's going to be pretty easy, just to checking that you have a pretty similar example. If you don't, then you might have to look and wonder why is that? What was the methodology that I created my initial train test validation? Is that the correct way to do it? And mostly, will this generalize again? If I push a model to production, should I see this same differing distributions? Think through whether that was representative, but also do it for the predictors as well. Maybe you saw a new class show up or something like that, and you want to be as careful as you can. So maybe use statistical tools to try and test the distribution at first. But yeah, I think at some point you do have to start taking a look if your third test set doesn't have reliable feedback. I mean, you also might want to go into your model. And as you develop an intuition, I can usually see if this is a very heavily fit model. I just have a feeling for that. If I have 3,000 trees going in on a GBM at depth 15 or something like that, that's a pretty heavy model. Maybe I want to scale that back just generally. It just might be a good idea. Even if the train and test were working out, you might want to scale that back. So maybe put more regularization on the GLM, so a less complex model, less neurons in a neural net. In deep learning or trees as well, maybe fewer trees. Random forest generalizes really well, actually. And maybe seeing what a random forest is a good idea as well. So yeah, no specific prescribed technique, but yeah, it's very tempting to try and look at that data. So we got 1 minute left. One more question, or we have the next speaker up. So. All right, cool. Well, who's next, Brandon?